All right. Welcome to 21A. This is our first lesson, and I'm going to put this videos up on YouTube now. And it's going to be based off all of the notes I already have on my website. If you're a student of mine right now, you should already know my homepage. I also will have it in the YouTube description. So ideally, I don't want to make these videos very long, so you should look over the notes yourself, and then if this is going to be just kind of a walkthrough of the notes as if I was in class teaching you. This is what I would be doing, because sometimes it's hard to learn just by reading the notes. It's helpful to actually hear what's happening. So okay, so hopefully you've looked at these notes already, and we're going to get started. So in the beginning of calculus, we're going to review first some of the important pre-calculus skills that you should have already learned in pre-calc. Two big ideas are the idea of the domain and range of a function. So quick review of that. If I've got a portion of a function here, let's say just between 1 and 7 here, the domain is the set of x values that my function takes on. One way to visualize that is if you can imagine smashing this graph into the x-axis, you would see stuff between x equals 1 and x equals 7. So there's your domain. Remember, you can also express something like this, a whole set of x values, in interval notation, which is what we're going to do a lot in calculus. So bracket 1 comma 7 means all of the x values between 1 and 7 and including 1 and 7. The range of a function is the y values that your function takes on. So similarly, you can imagine smashing this graph into the y-axis, and you would see something everywhere on the y-axis between 2 and 8. So there's your range, and that's what it looks like in interval notation. Okay, scroll up here. Even and odd functions were something we talked about in pre-calculus. So let's review that. F of x equals x squared is a good example of an even function because, and what makes it an even function? Well, there's symmetry involved, right? If you plug in -1 to x squared, you're going to get the same value as f of 1. You're going to get 1 for both of those. If you plug in -2 for x, you're going to get the same value as +2, right? 4 for both of those. And that's going to work for every x value. So the definition of an even function is f of -x always gives you the same as f of +x. That's how you tell if a function's even. Graphically, of course, because of that, because you get the same y value for every x value and its negative counterpart, you're going to always get symmetry about the y-axis when you're looking at an even function. Okay, and then we have odd functions. F of x equals x cubed is a good example of an odd function. And what makes it odd? Okay, let's think about it with numbers. If you plug in f of 1, you're going to get 1. If you plug in f of -1, you're going to get -1. You're going to get the opposite of the y value. F of -2 is going to be the opposite of f of +2, right? You get -8 for -2, and you get +8 when x is +2. So the definition of an odd function is f of -x, any negative number you plug in, is going to be the opposite of f of +x. That's what makes something an odd function. Now there's symmetry involved as well for odd functions, and the way it usually gets described is we say that odd functions are symmetrical about the origin. And what that means is, if you can imagine taking this right half and first reflecting it around the y-axis over here, and then reflecting it around the x-axis, you would get this part. And you could do it the other way. You could revolve this around the x-axis and then the y-axis, you would get that. So you could think of it either way. That's symmetry about the origin. So there are some other, sorry, I'm going to make everybody dizzy. There are some other common odd and even functions that you know about. The cosine function. Cosine, if we graph cosine, starts up here at 1. We usually only graph it for positive x values, but if you went into the negative region for x, you would see you're getting the mirror image, right? And so cosine is an even function. The cosine of negative x is the same as the cosine of positive x, so that's an even function. Sine is an odd function, right? If I extended sine in the negative direction, I can see that the value of the sine of a negative angle would be the opposite of the sine of the positive angle. Okay, so sine of negative x is equal to the negative sine of positive x. Okay, how about tangent? Well, what's it look like? This is our graph of tangent. If you plugged in a negative value, you're going to get the exact opposite as the positive value. So tangent appears to be an odd function. One way you could prove this, though, and this is going to become important too at some point, is remember the test for an even or an odd function is to figure out what happens when you plug in negative x. Because tangent is made up of sine over cosine, f of negative x is the sine of negative x over the cosine of negative x. We already know sine is an odd function, so the sine of negative x is the negative of the sine of positive x. Cosine's an even function. The cosine of negative x is the same as the cosine of positive x. So if I then take this one negative and put it out front and rewrite this as tangent, what have we shown? We've shown that the f of negative x is the negative of f of positive x, right? You're going to get the negative of tangent of x. And one of the things there's so many things to talk about when we, talk about pre-calculus. What I wanted to start to do with this first set of notes is to kind of use these ideas of domain and range and odd and even functions to graph some trickier functions. And in doing so, we're going to kind of subtly stumble upon some ideas that we're going to be using in calculus. Okay, so here we go. Now this first one, not so much. You should recognize this as an upside down parabola, raised up 9, opening downward. Parabolas, we're going to be graphing those. You should know how to graph those by hand. As far as the domain goes, 2 ways to think about it. One way is to think about, is there any limitation for what I'm allowed to plug in for x? No, right? I can plug in anything I want for x and do 9 minus x squared. So my domain is any x value from negative infinity to positive infinity, which in interval notation looks like that. Okay, you would want to use parentheses here because you can't include infinity. That's infinity doesn't have an endpoint there. The other way to view the domain, I told you before, was to smash it into the x-axis. And if you can imagine smashing not only this part, but the part underneath here, you hopefully could see that you would get stuff everywhere, right, on the x-axis. So that's another way to view the domain. For the range, if you smash this function into the y-axis, you're going to see stuff all the way along the y-axis up until you get to 9. So your range would go from negative infinity to 9, including 9. You would have something there. And then the idea of, of course, the symmetry of this definitely looks like an even function, but it's good to be able to prove that. So if I plug in negative x into this function and I square it, I actually get the same thing, right? I get 9 minus x squared, which is the exact same thing as my original function. So that shows me that is an even function. Okay. A little more complicated here. All right, so this function, that's a 9. That's the square root of 9 minus x squared. I don't know if I made it worse there or not. Um, if you're not familiar with that function, we can start by finding the y-intercept. If x is 0, y would be the square root of 9, which is 3. X-intercepts are when you set y equal to 0. And if I set this equal to 0 and square both sides, hopefully you can see that x could be plus or minus 3. Okay. The domain. Now, okay, again, this is hard because I'm doing my pre-written notes. I've already got the graph there. But if I didn't have that graph, how would I have found the domain? Remember that in this case, I can't just plug in anything for x. Stuff under my square root has to be greater than or equal to 0. I can't take the square root of a negative number. So I would have written 9 minus x squared greater than or equal to 0. And recall that the way to answer that, if you can't just look at that and see what x values you're talking about, the way to answer it is to factor it and use a number line. -3 and +3 make both of those factors, well, one of those factors equal to 0. And then we pick test numbers, right? If I try -4, 3 minus -4 is positive, 3 plus -4 is negative. So I know that when x is -4, that's negative. If x is 0, they're both 3, that's positive. And if x is +4, you're going to get a negative value because 3 minus 4 is negative. Greater than or equal to 0 means the positive values. So my domain for this one would be between -3 and 3. Okay. Now, how do I figure out the range if I don't know what the graph of the function looks like? And this is a trickier thing. To find the range of a function, there's a few techniques, but honestly, the best way to answer the range in this technique is to just think about it. In this problem is to just think about it. I want to think about what's the smallest output I could ever get out of this square root function. Can you see that if x was 3 or -3, you're going to get 0 under that square root, and 0 is the smallest thing you could ever take the square root of. So my smallest value is going to be 0. My largest value, if my function is 9 minus x squared and I'm looking for the largest value, the best option would be to have x being 0, right? So you're not subtracting anything from 9, in which case you get the square root of 9, which is 3. Okay, so my range is between 0 and 3. All right, okay, there's the function again. Now, it is even as well, because if you plug in -x, you're going to get the exact same thing as +x. Now, in fact, this graph right here is actually the top half of a circle. And one way to show you that is that if you write that as y equals the square root of 9 minus x squared, square both sides, move the x squared over, you should recognize that as a circle with a radius of 3. However, the original problem, because it's the square root, square roots can only come out to be positive, which is why it's just the top half of that circle. It's not the whole circle. Okay, I'm going to stop this video and we'll continue in the next video.